Start the recording. Now, just a reminder that the homework one is due tonight at 11:59 p.m. If you have any questions related to the homework, please feel free to ask questions after the class. I know that Monday was a holiday, so you could not have the office hours. So if you have any questions related to the homework, please feel free to ask after the class today. Okay. All right. And of course, there were a few questions related to labs again. So we are starting the labs on September 15th. That's almost 2 weeks from now, like 1.5 weeks. But I hope that you'll be able to get all the parts by that time. Or many of you have already gotten all the parts required for the lab. Okay. All right. So we have been discussing AC amplification for last 1 or 2 lectures. And you know that the basic function of an amplifier is to increase the AC amplitude of the signal. And again, I have highlighted AC because I want to emphasize that the job of an amplifier is to amplify AC signals, not DC signals again. All right. Of course, the output shape will be identical to the input if the amplifier is linear. So we'll talk about more in terms of linearity and what does linearity of the amplifier mean. But again, as you know that the output versus input characteristic, if that is linear, then we say that the amplifier is linear, which means that the shape is preserved from the input to the output. If the shape is not preserved, then the amplifier will be called a nonlinear amplifier. And we also started discussing a little bit about voltage transfer curve or voltage transfer characteristics of an amplifier. In today's lecture, we'll see why, as your input voltage increases, your output voltage decreases in most of the amplifiers or many of the amplifiers. And this will be called a transfer curve because it gives you the transfer functions from the input to the output. You have your input voltage and you have your output voltage. The transfer function from the input to the output is basically represented in the graphical form in the VTC or voltage transfer characteristic. Now, in general, it will be called a transfer curve whenever you're talking about input and output and graphically representing the relation between input and output. In this case, both input and output are voltages, and that's why we call it a voltage transfer curve or a voltage transfer characteristics. And it is, in short, it's called VTC. So in many of the circuit design classes, you'll hear about VTC a lot. And this is what VTC means. Okay. Now, what does an operating point mean? So as we were discussing a little bit at the end of the last lecture, that again, I'll explain why the output is reducing as your input is increasing. But what would be the gain of this particular VTC? Because you know that gain is, okay, let me see if I can annotate. So gain, which is, I'm talking about AC gain over here, and that's going to be the AC voltage at the output divided by the AC voltage at the input, right? So your dV out, that is the small variations or small fluctuations at the output divided by dV in, that's going to be your gain, right? In terms of AC, in terms of small AC signals. And we'll discuss more about small signals in today's lecture. So if this is your gain, that a small fluctuations in your output voltage divided by a small fluctuation in your input voltage, if that is gain, you also note that this is basically the derivative of your output with respect to your input, which is also the slope of this VTC. dV out over dV in, that's the slope of this VTC, correct? So you know that if the slope is high, the gain will be high. And here by high, I mean the absolute value. Of course, you know that in this case, the way the slope is drawn, the slope is negative in this case because this angle is more than 90 degrees. So of course, the slope is negative mathematically. But if you think about the absolute value of the slope as the gain, then you want to have, or if you want to extract the maximum gain out of the system, you want to be at a point where your slope is maximum in absolute value again. So where is the slope maximum in absolute value? So of course, here the slope is 0 because your output is not changing at all as your input is changing. Here again, your slope is 0 or your gain is 0 because your output is again not changing or changing by a very small amount as your input is changing. On the other hand, if you are here, then your output is changing significantly as your input is changing by a small amount. And if the ratio of change in output divided by change in input, in other words, the gain, so let's take the absolute value of this and call that the gain. So absolute dV out over dV in is basically your voltage gain AV. Of course, the voltage gain in this case is negative. Why it is negative? Because again, the output reduces as your input increases. So there's an opposite relation between your input and output, a 180-degree phase difference between your input and output. And that's why the actual value of gain is negative in this case, but the absolute value is what we are interested in at this point. So if you want to have a high gain, you want to be somewhere over here where your gain or the slope is high. And if you think about it, it is probably best to start from a point which is exactly at the middle of this region where your slope is high. So this is what we are doing in this curve at the bottom. So again, V out over V in, and you are drawing the VTC once again. But at the same time, what you are doing here is that you're applying a sinusoidal V in. So for example, over here, you see that there is a sinusoidal V in that is being applied. And because the gain over here, the slope over here, the absolute value of the slope is more than 1, your gain is more than 1. The absolute value of the gain is more than 1. And what that will translate into graphically, if you just follow these dotted lines, what will happen is that as your input is here, your output is at this point. If your input increases by a small amount, you can again draw this dotted line. You'll find this point on the voltage transfer characteristic, extend that on the horizontal direction, you'll end up with this point, which will be your output voltage when your input voltage is this much. Again, if your input voltage is at the peak of this sine wave, let's say over here, again, draw these dotted lines, extend it on the horizontal direction according to the graphical representation, and you'll end up with this trough or the minimum point on the output sine wave. Now, because as your input is increasing, your output was reducing, you see that there is a 180-degree phase difference. So if your input increases, output reduces. So if your input looks like a sine wave, which has a positive cycle at the beginning, your output will look like a sine wave, which has a negative cycle at the beginning. And that is what meant by having a negative gain. The negative gain does not mean that the value of the signal becomes negative. Right? If you apply let's say a 10 millivolt AC, at the output, it does not become minus 10 millivolt. And there's no meaning of a minus 10 millivolt there. But what minus 10 millivolt means is that it's the same 10 millivolt, but with a 180-degree phase shift. So if your sine wave of the 10 millivolt had a positive cycle first and a negative cycle after that, at the output, you'll first have the negative half cycle and then the positive half cycle. That is what is meant when you say my gain is negative. All right, and this point, this middle point, which corresponds to the DC value or the average value of the sine wave, right? So you know that if you have a sine wave, there's always a DC potential around which you draw the sine wave. Now, this DC potential is going to be called the Q point or the quiescent point. The meaning of quiescent is something that is not changing. The DC value is not changing. It's the AC that is changing over on top of that DC potential. So that's why this Q point, the average value of the sine wave, if you take the average of the sine wave, it is 0, of course, but that 0 is like just in terms of AC 0, but it could be on top of a DC value. Why I'm saying it could be on top of DC value? Because the absolute 0 voltage is over here, right, at the origin. The absolute DC 0 is at the origin. Your signal is not at the origin. Your signal is at some positive DC voltage, and then you have a sine wave on top of that positive DC voltage. That positive DC voltage is going to be called your Q point or the operating point or the quiescent point. And this is also called the bias point. Why bias point is important? Because you want to be at let me clean all this up. You want to be at a point to start with where you expect gain. You do not even expect gain if you are here. You do not even expect gain if you are here. But you expect gain if you are in this region. So the first job for an amplifier, for you to make an amplifier work, is that make sure that the amplifier, the input voltage is biased at the correct point, correct Q point. And that is also called the biasing point. The biasing means that instead of applying a 0 DC potential, you're applying your sine wave around a non-zero DC potential. And that non-zero DC potential's value is your coefficient point or the bias point's value. And the whole idea is that you want to be at a point on this voltage transfer characteristic where your absolute value of the slope is high. Because that's when you expect gain. You don't expect gain anywhere else. Okay. Now, why the curve looks like this, why there is no gain over here and why there is no gain over here, we'll understand that when we start discussing MOSFETs. But this is how the VTC of, in general, any amplifier looks like. Okay. All right, so you already know that the slope of the VTC, or basically a tangent drawn to the VTC at the Q point, is going to be the voltage gain of the amplifier. Now, if that voltage gain is AV, the voltage gain, 20 log base 10 of that value is going to be the voltage gain in dB. You know about decibels, right? It's just a scale of like representing things in a logarithmic scale. So 20 times logarithm to the base 10 of AV is going to be called the voltage gain in dB scale. Now, if you think about amplifier's linearity now, it should be very easy to understand. Again, just looking at the voltage transfer characteristic. That the amplifier's linearity, when you're considering, let's say, sinusoidal input, an amplifier will be called linear if whenever your input is a sinusoid, that is a single frequency, your output is also a sinusoid with the same frequency. So you do not expect any distortion. The input, the way the input curve looks like, the input signal looks like, the output signal should also look like the same. It's just that it can be an amplified value in terms of the amplitude. That's what you expect from the amplifier, right? And that requires your voltage transfer characteristic to be linear. Here, as you see, that the voltage transfer characteristic is not linear all the time, right? Linear means that it would exactly look like a straight line. So everywhere, if it is a straight line, then it's linear. But you see that the voltage transfer characteristic becomes non-linear in this region and this region. So again, you want your amplifier to operate in this region. Let me draw it with a rectangle. So this region is where you can kind of approximate the VTC to be linear. That is, the amplifier's transfer function can be approximated as a linear transfer function in this region. And again, as you know that if you want gain out of the amplifier, you are interested in that region anyway. So that's where you want your amplifier to be. There are two advantages, that the amplifier is linear in that region. Also, the amplifier provides a high gain in that region. If you're in anywhere else, you'll not see a gain, and of course, you'll not be linear. And that is the whole purpose of biasing. Biasing means that you want to be a region where you can expect gain and you expect the amplifier to be linear. Questions? That's a good question. That's a good way to understand it. The question is, at the Q point, is the input AC signal 0? That's right. So if you look at this curve at the bottom, the average value of this input signal, right? So let's say average value of any sine wave is 0, right? So if the sine wave is around a 0 DC, if this point is a 0 DC, then you say the average value of the sine wave is 0. If this point's voltage is, let's say, 2 volts, so instead of 0 volts, so you say a 2 volt, and on top of 2 volt, you have a sine wave. Then the average value of the sine wave is 2 volts, right? So that's all we are saying here, that instead of this point, the Q point being an absolute 0 value, you have a DC value. So you want to have the absolute 0 is here at the origin, right? The absolute 0 is at the origin. You want your operating point of the amplifier to be at a point where you expect gain and linearity out of it, and that is the Q point, which is most likely going to be at the middle of the VTC. Of course, this VTC can shift a little bit left and right, up and down, depending on not up and down, but let's say left and right, depending on the choice of your amplifier. But in general, if you're let's say at the middle of the VTC, you can expect it to be linear as well as having a high gain, just by looking at this curve, right? Yeah. Okay, so this is just mathematically representing it, that you have the power supply, you're drawing the energy for amplification from the power supply. Your slope is dV out over dV in at the Q point. So your slope, which is dV out over dV in at the Q point, which is over here, that is your gain. If you move your Q point, if you can always move your question point. So let's say you say, instead of operating at this point, I'll apply my input over here. So let's say this point is where I'll have the DC value of my input. So my operating point will become this. It will still probably be linear, but the range of that linearity will reduce, because you see on this side, if you just go a little bit, then you're in the nonlinear region, whereas you have a large region to use on the top side. So that's why I said that try to be at the middle of your VTC. In that way, you'll have almost equal amount of voltages or regions of voltages to use on the top and the bottom of the VTC. Okay? So that gives you the maximum amount of linearity, which will be clear when you see some examples. And this is what is called a bias, right? That you're biasing your input not to be at zero, but at some non-zero DC point. That is what is meant by biasing. And automatically your output, because your VTC looks like this, automatically if you set an input bias point, you'll have an output bias point as well. Even without any AC voltage, application of any AC voltage. Let's say you just apply a DC voltage at your amplifier's input, the amplifier's output will have a DC voltage which will be equal to this. Okay. Now, some nomenclatures. It's general. I see a lot of students. Even when I was a student, I used to get confused with the nomenclatures. So I just want to have a slide on this, that whenever you're discussing any AC quantity, let's say AC currents and voltages, you will generally see that it's written with a lowercase letter. So currents represented with I, it could be I at point D. And these are basically for MOSFETs and BJTs, the drain, source, gate. We'll discuss all of those later in the class. But let's say for any node which is represented as D, S, G, or any other letter, everything will be represented with lowercase representation. Whereas voltages, again, lowercase representation, VD, VS, VG, etc. The DC quantity generally represented with uppercase letters. And if you have both AC and DC, you might see a mixture in books. Some books will follow a nomenclature like this, that you have the current in lowercase I, but the node is represented in uppercase, or the current is represented in uppercase and the node is represented in lowercase. So that's how they differentiate between the scenarios when you have AC, DC, and AC plus DC. So whenever you're seeing something in lowercase, that is going to be a AC quantity. And uppercase will mean DC quantity. A mixture of that will mean a combination of AC and DC. Now, amplified small signal model, which is something we already discussed, and your homework 1 already has a version of this small signal model of the amplifier. We'll discuss why is it called a small signal model as well. But you already know that if you are applying a input voltage, in the simplest model, you can have that AV0 times V in, where AV0 or AVO is your voltage gain, times V in will be available at your output. Of course, because this is a dependent voltage source, it can have a non-ideality in the form of a series impedance or a series resistance that is represented with the Z out. On the other hand, if you want to make the circuit a little bit more complex, you can have something like this on the right-hand side, where you have an input voltage and you have a Z in. You have a non-infinite. Basically, you have a finite input impedance. A real op-amp will always have a finite input impedance. An ideal op-amp will have an infinite input impedance. So on the right-hand side, what you see is the real op-amp, or a representation of a real op-amp in terms of the input impedance. And here you see a finite input impedance and a non-zero output impedance again. Now, this is a small signal model, which means that small signal generally means AC. So maybe I can probably jump a few slides here just to represent this. That why is it called a small signal model? This is called a small signal model because look at the right-hand side diagram. It's again your VTC, your voltage transfer characteristic. If your input voltage is large, if your input, instead of being this sine wave, if I have a sine wave which is, let's say, this large, okay, I can choose to have a sine wave which is large, right? What would happen in that case? That if you again draw these dotted lines, your Q point or your quiescent point will be over here. But let's say the peak of the sine wave is somewhere over here. That's why it crosses the voltage transfer characteristic. Again, the trough of the sine wave at the input, if you draw this dotted line, you'll see that it crosses your VTC somewhere over here. So it already goes in the nonlinear region. So at the output, what you might see is something like this, that you go here and then you see a clipping, then something like that, and then again here you see some amount of clipping. So in that case, you see that your input and output does not look similar. Input looks like a sine wave, output looks like a clipped version of a sine wave. And as soon as that happens, you cannot call your amplifier a linear amplifier anymore, because for linearity to be valid, your input and output shapes should look the same. So if your input voltage is large, your amplifier can go out of the linear region on the VTC curve. That's why the input needs to be small. And it makes sense, right? Because if you want to amplify something, the problem was it was small. That's why you want to amplify it. If the input was already large, what is the need to amplify it? Right? So because the input was small, you want to amplify it. And that's why the model of the amplifier is generally called the small signal model. The AC model of the amplifier is called the small signal model, because your input is supposed to be small. If the input is large, there is no need to amplify it. And that is why the small signal model is sometimes called AC small signal model. You might see this term in books as well. Questions? Exactly. So because I skipped a few slides, so don't look at this right now. I'll be explaining that. But again, you know the Thevenin and Norton equivalence. It's basically your homework problem 4 and homework problem 5. They are talking about the same thing. It's just the Thevenin and Norton equivalence that, yeah, you can represent this dependent source either as a voltage source or a current source. 2 slides back, it was shown as a voltage source. That was the Thevenin equivalent. Here it is being shown as a current source, which is the Norton equivalent of the same thing. All right. So keep in mind that why do we call it small signal? And whenever anyone talks about small signal, you know that you're talking about AC analysis. You're talking about an AC signal which is small, and you're trying to analyze the circuit in terms of the AC properties. Okay. So going back those few slides. So the AC small signal model, that's why it is valid only near the Q point, because you want your input signal to be small. You want your input signal to be small. So the fluctuation is by only a very small amount around the quiescent point. Around the original DC biasing point, you are varying only by a small amount, maybe a millivolt or 10 millivolts, which is a very small number, right? So the small signal model that you see is also valid near that Q point, near that quiescent point or the biasing point. All right. And again, as the question was asked, that here you see a Thevenin equivalent model where you are representing the voltage gain times V in, and you have a series resistance over here. You could have represented this as transconductance times V in with a current source and then a parallel resistance. That would have been the Norton equivalent circuit, which is your homework problem 5 in your homework 1. All right. Now with the small signal model, this is again basically your homework problem number 4, which we discussed in the last lecture as well, that any voltage source, let's say this voltage source on the left side, that will also have some amount of non-ideality. Let's say Z source is the series resistance of that voltage source. So of course, there will be a voltage division at the input side. So you take care of that voltage division at the input side, multiplied with AVO, which is the gain of the op-amp, multiplied with a voltage division at the output side, because this dependent voltage source will also have a non-ideal series resistance, and then it will have a voltage division with the output Z load, the impedance connected as the load, right? So that's why you see this first term, which is a voltage division at the input, times the voltage gain of the amplifier, times the voltage division at the output. That becomes the overall voltage gain of the entire system. So just for the amplifier, you have AVO, That's it. That's just the gain of the amplifier. But the overall system can have a very different gain because of these non-ideal voltage divisions at the input and output. All right. Just an example, similar to your homework problem 4, if RS is 1 kilo ohm and RIN is 9 kilo ohm, you have a voltage division at the input, which is 9 kilo ohm divided by 9K plus 1K. So 9 upon 10. So 0.9 is the voltage division ratio at the input. Your AVO is, let's say, 100. The voltage gain, so there is a typo, so it should not be AVO. Like AVO should be equal to 100. AVO times VIN is 100 times VIN. So AVO is 100. And then at the output side, it is a voltage division of RL and ROut. So you have RL divided by RL plus ROut at the output side, which is again 1 kilo ohm divided by, again, I believe there is a typo here. So let me just correct it right now. So this should be 1 kilo. And let's say this is, let me just for the sake of correctness, I'll be changing this. So AVO times VIN is basically 100 times VIN. And this value is 1 kilo ohm divided by 1 kilo ohm plus 0.25 kilo ohms. And that gives you the ratio 0.9 times 100 times 0.8. The numbers are correct, but it's just that there was a typo over here. So this will be equal to 72. So as you see that even though the amplifier has a gain of 100, the whole system has a gain of only 72, right? Now, if you want to represent the gain in dB, this is just a table. You don't need to remember it. But again, if you put the values in your calculator, you'll see what is the meaning of it. So because when you're representing the gain in decibels, the formula is 20 times log base 10 of V out over V in. However, the original formula of bells and decibels. So what is bell? The bell was logarithm of your output power divided by input power. That is defined as the bell unit when you're talking about the logarithmic gain. Output power over input power, and you take a logarithm to the base 10 for that. So that was bell. So if you're talking about power, power is, you can represent power as V squared over R or I squared times R, as you know from your high school physics or undergraduate classes, that power is directly proportional to the square of the voltage or square of the current, right? So that's why you see that when you're talking about power, you can represent it as V out squared divided by V in squared if you're talking about a ratio of powers. Ratio of voltages will be V out over V in, but the log, okay, let me just use my pen over here. So V out squared over V in squared, that's just the ratio of powers. You take a logarithm for that, that becomes the unit of bell. Decibel means 10 times of that value for which you get the unit of bell. So 10 times log of V out squared over V in squared, that's your decibel. Now, as you know that the property of logarithm is that if you have a square term inside, you can take the 2, that the to the power 2 outside, and it will become 20 times log base 10 of V out over V in. So that's how the formula actually came in, that why do we say that it is 20 times log of V out over V in when you represent it in terms of decibels. And then again, if you have a voltage ratio of 10, I mean, I'll not go through this table. You can just put, you also don't need to remember the table. But if you put these values in your calculator, that's what you'll get. That if your voltage ratio is 10, your decibel equivalent value is 20 dB. If your voltage ratio is 1, it's equivalent to 0 dB. If your voltage ratio is 0.1, your equivalent dB scale value will be minus 20 dB, and so on. Right? You can just put those values in your calculator and check, but this is how it will look like. A value of 100 is 40 dB. A value of 1,000 is 60 dB. 10,000 is 80 dB, and so on. So every decade, every 10 times that you increase your value of the ratio, you'll increase your decibel value by 20 dB. So value of 1 is 0, value of 10 is 20 dB, value of 100 is 40 dB, value of 10,000 is 80 dB, and so on. And same thing happens on the opposite direction as well. The value of 0.1 is minus 20 dB, a value of 0.01 will be minus 40 dB, and so on. Something that is interesting is that if you have a voltage ratio of 1 over square root 2, that is 0.707, which is equivalent to having a power ratio of half, because again, you square your inputs, both the numbers, you get a power ratio of half, right? The value in that case is -3. Now, why that is interesting and why you may have heard about this is that whenever you talk about bandwidth of an amplifier, you may have heard about a -3 dB bandwidth in your previous lectures, right? So what does -3 dB bandwidth mean? That you may have, let's say you have a gain of, I don't know, let's say 40 dB. Let's say you have a gain of 40 dB at low frequency regions, and then the gain reduces at higher frequencies. That's what bandwidth means, that you can only support gain up to a certain frequency, and after that your gain drops. Now, if your low frequency gain is 40 dB at 37 dB, which is 3 dB below your low frequency gain. So 3 dB below, that means this -3 dB number. So 3 dB below your low frequency gain, you have a voltage ratio of 1/√2, and you have a power ratio of half. And that's why sometimes it is called a half power bandwidth. Again, this name might sound familiar, half power bandwidth. That really means that you're talking about the -3 dB bandwidth, which is 1/√2 times lower than the voltage value in terms of the low frequency to that particular point's voltage. In terms of power, it is half power. Okay, so remember that this is maybe one of the interesting numbers that you may need to remember, that if you're talking about half power, it's basically a -3 dB, and that is equivalent to 1/√2 in voltage ratios. Okay, all right. So now let's address the elephant in the room, that if we have an amplifier, why did I say that my output voltage will reduce as my input voltage is increasing? Again, we'll discuss in much more detail later, maybe during lecture 20, lecture 30, around that time in detail. But this is how a very simple MOSFET-based amplifier looks like. So this is one circuit element, which is called a MOSFET, metal oxide semiconductor-based field effect transistor. You don't need to worry about the full name right now. We'll discuss that in detail. So MOSFET is one type of transistor. And the job of the MOSFET is that it will act as a voltage-controlled current source. BJTs, which we'll also learn in the class, BJTs are bipolar junction transistors. Again, you may have heard about the name. BJTs are a current-controlled current source, whereas MOSFETs are voltage-controlled current sources. So in terms of their underlying physics, they are different. For a BJT, the output current is controlled by the input current. For a MOSFET, the output current is controlled by the input voltage. That's the basic difference between MOSFETs and BJTs in terms of the underlying physics. So if your MOSFET is a voltage-controlled current source, which means your output is current and your input is voltage, what kind of an amplifier is that? If your output is current and input is voltage, it's a transconductance amplifier, right? The transfer function is a conductance, going from input voltage to output current. So MOSFETs make a very good transconductance amplifier. So this is how the MOSFET-based amplifier looks like, a very simple version. I'm not talking about complex structures right now. The very simplest version of a MOSFET-based amplifier looks like this, which you see on the bottom left. You have an input voltage provided to a terminal called a gate, and the gate is that control terminal. And then there are two other terminals called drain and source, between which the current actually flows. Again, we'll look into the details of these terminals and how they behave later, but the current is actually flowing between these two terminals from VDD to your ground. And the gate terminal acts as a control terminal. So how much current will flow, that will be controlled by the gate terminal. That's how it will eventually behave. And that's why you call it a voltage-controlled current source. That how much current will flow between the drain and the source will be controlled by the voltage at the gate. For a BJT, it gets controlled by the current at the base. Right? So just like the gate terminal over here, there is a terminal called base in a BJT, and that terminal controls how much current will flow at the output. We'll learn all about that later. Now, what is important at this point to understand is that this is a transconductance amplifier. Okay, so your output current is GM times VI. So output current is transconductance times input voltage. Right? We can write this very simple equation. Now, when your input voltage is small, your output current is also small, and your V out, which is VDD times. So what is your output voltage over here? Let's say this is your V out. And if this is VDD and there is a current flow of ID, let's say there is a current flow of ID, there is a resistance RD over here, and this point's voltage is the output voltage for the amplifier. So what is the output voltage? Output voltage is always going to be VDD minus ID times RD, right? Why? Because ID times RD is the voltage drop across this resistance according to Ohm's law. If the current is ID, resistance value is RD, the voltage drop across that resistance is ID times RD. So the output voltage at this point, at the bottom terminal of the resistance, is VDD minus ID times RD. So when your VI increases, when your input voltage increases, your current also increases according to this equation, ID times GM VI. Your ID increases as your V in increases. Your V out, which is VDD times ID, VDD minus ID times RD, that will reduce. Because if your input voltage increases, your current will increase. If your current increases, your output voltage will reduce because the current times RD is having a subtraction term over here, right? And that is the reason why we drew this kind of a VTC. As your input voltage was increasing, your output voltage should reduce. Because as input voltage increases, your output current increases. If your output current increases, your output voltage reduces. According to Ohm's law, in this particular case, right? Okay, so this is just again the small signal model representing the transconductance. So again, this was coming back to your question that, okay, we could have represented the dependent source as a voltage source as well. But because the MOSFET is a transconductance, MOSFET converts the input voltage to an output current, it is more appropriate to represent it with the Norton equivalent circuit. Because your output, in terms of the physics, the output is the current. And that's why you represent your MOSFET amplifier small signal model like this, that you have your input voltage. This RS is the non-ideality of that input voltage source. Then you have a Z in, which is the input impedance. And we'll see when you discuss MOSFETs that Z in is very, very large. The gate is actually built, there is an oxide layer inbuilt into the gate. And because of the oxide layer, which is an insulator, the oxide layer over here at the gate, we'll discuss this later. Don't worry about it right now. But the gate will have an insulating oxide layer, which means that no current can go in. And because no current can go in, the input impedance is very large. Now you can probably just relate it back to your op amps that you learned in 3111, that op amps had an infinite input impedance. So you can directly probably guess that inside the op amp there are these MOSFETs with the gate of the MOSFET directly connected to the input of the op amp, and that is the reason why it has infinite input impedance. We'll look into that later in detail, but I just want you to think and relate with that concept. Okay, so your Z in is very large. Here you see the Norton equivalence for the dependent source, and your RO for this dependent source needs to be very large, right? Because for any ideal current source, you know that the parallel resistance needs to be a large one. Okay, now in this case, what would be interesting is that if you want to represent the voltage gain, the overall voltage gain of the systems, what would be the overall voltage gain of the system? Of course, you have a voltage division at the input side. That voltage division is this Z in over Z in plus RS. That's the voltage division between these two resistances. Then you have everything that is connected over here. So what is connected over here? Of course, you have this GM times VGS, which is the current source. Then you have an RO in parallel to that, because any current source should have a non-ideality that is a parallel resistance connected to the current source, right? And then think about the previous slide. Maybe I can also go back to the previous slide, that at the drain node, you had a RD resistance connected, and that RD, the top terminal of that RD was connected to VDD. So let me just go back one slide. So at the drain node, which was your output terminal, you had this RD resistance connected, and that was connected back to VDD. The top terminal of that resistance was connected back to VDD. So now if I go one slide forward, at the drain terminal, which is over here, you connect that RD resistance connected to VDD. Okay. And your output is between this drain terminal and the source terminal. The source terminal is grounded. If you go back here, this is called the source terminal, which is grounded. And in the model, the source terminal is here, which is basically representing your ground. So your output voltage is the voltage between your drain terminal and the source terminal in a way. In the previous case, in this case, your output voltage is basically the voltage at this terminal. Source is already grounded. So it's basically the voltage at the drain terminal. That's your output. Now, what is interesting here is that you have an RD connected to VDD. Because we are talking about a small signal model, and this will be a very, very, very important concept for this class or any other analog design class that you take in future. So what I'm going to say is going to be very, very, very important for that. So you have this VDD connected at the top terminal. Let me see if I can use a pen. So you have the VDD connected at the top terminal of the RD resistance. And VDD is a DC voltage, right? Now, something that I said in the first lecture or second lecture, that any DC quantity is an AC ground. Any DC quantity is an AC ground because the AC voltage on a DC is 0. If you talk about a 5-volt DC, it's 5-volt fixed voltage. There is no AC component. So the AC component on the DC voltage is 0. So any DC voltage in terms of AC is a ground. So your VDD, even your VDD, which is a DC voltage, ideally a fixed DC voltage, that is a ground in terms of AC. So that is a very important concept that you should remember, that even your supply is a ground in terms of AC. So this is a concept which might seem a little hard to grasp at the beginning, but think about it. We are not talking about the absolute voltage when you're talking about AC analysis or small signal analysis. So when you do a small signal analysis of a circuit, you're only talking about the AC voltages and currents. So whatever is DC is as good as ground to you because there is no fluctuation in any DC voltage. And that is the reason why this upper terminal of RD, which is connected to VDD, and if I say my VDD is a AC ground for this purpose, or a virtual ground, that is another name for this would be virtual ground. And you know about virtual ground concept from your op-amps. And this is what it really means, that it is not an actual ground. But for this AC analysis, virtually this is as good as ground because there's no AC component on your VDD. So your VDD is actually virtually connected to the ground terminal for any kind of AC analysis. What that means is that this RO resistance, which is across the transconductance, and this RD resistance, which was otherwise connected at the top, like from drain toward the top, it was connected like that. But in terms of AC analysis, because this VDD node and the ground node is same, there is absolutely no difference in terms of AC for those two nodes. RO and RD comes in parallel now. See, the top terminal of RO and the bottom terminal of RD are same. The bottom terminal of RO was ground. The top terminal of RD was VDD. But because VDD is an AC ground, in terms of AC, those two terminals are same. And that is the reason why your RD comes in parallel with RO whenever you're doing any kind of AC analysis. We'll see a lot of examples like this in future, but I just wanted to make sure that I emphasize why your supply is considered as an AC ground. And that's because on your supply, there is no AC voltage. There cannot be any AC voltage on your supply, so it's as good as ground, just in terms of AC. Okay. Again, it's not an absolute value ground, but virtually you can consider that as your ground. So if that is something that we can assume, then what is the output voltage now? So you have GM times VGS, that's the current that flows here. You have RO, and let's say you put the RD in parallel, just to simplify things, so you don't need to draw this anymore. So you have GM times VGS, that's the current flowing in this direction, and the resistance in parallel to that is RO in parallel with RD. So the voltage at this node is going to be minus of GM-VGS times RO parallel with RD, which is again very similar to your homework problem number 5. Minus GM-VGS and minus because the current flows in this direction and you want to find out the voltage here, which is actually the opposite direction. So minus of GM-VGS times RO parallel with RD, that's the voltage at this drain node. And of course, if you consider the RS and the Z in this voltage division, then you will have the Z in over Z in plus RS, this term as well. Now, if you want to find out only the voltage gain, which is basically V in over V, or basically V out over V in, then this is what you get, the input voltage division over here, and the GM times RO parallel with RD, that term over here, because this is your, let me write that down. This is my V out equal to minus GM times VGS times RO parallel with RD. Now VGS, which is here, is equal to minus GM times Z in divided by Z in plus RS. So I'm writing down the voltage division at the input side. So Z in divided by Z in plus RS times V in times RO in parallel with RD. Right? That's the entire equation. So that is V out as a function of V in. Now, if you take V in on the left side of the equation, you get V out over V in. That is basically your voltage gain. And that is going to be Z in divided by Z in plus RS times GM times RD in parallel with RO. Now, if your Z in is very high and RD is much lower than RO, because RO is a resistance in parallel with the current source. So ideally, it should be an infinitely large resistance. So if RO is very high as compared to RD, then RD in parallel with RO is just going to be RD. So GM times RD in parallel with RO just going to be GM RD. And of course, this first term, if your Z in is very high, infinitely large, so let's say Z in is very large for a MOSFET, in that case, this first term will also go away. So your gain, voltage gain will be very close to GM times RD. If you make those approximations, if you cannot make those approximations, if your Z in is not very large, if your RO is not much larger than RD, then of course this is the exact form of the equation, and this is the approximated form of the equation. Okay, so that's about your MOSFET amplifier. Why small signal? We already discussed, because you want linearity in the amplifier. And looking at the VTC, you know that the input has to be small to make sure that the amplifier is linear. BJTs, bipolar junction transistors, for them, the Z in is not as large as MOSFETs. And again, we'll discuss this in detail. But the reason is that there is a current at the input. For BJTs, there is an input current flow. There is no insulator at the input terminal of the BJT. For a MOSFET, there is an insulator by design. Physically, there is an insulator. And because of that, no current can go in a MOSFET. But for BJTs, current can go in. So you can model the BJT, like just from a physics-based model, you should model it as a current-controlled current source. The output is a current. The input is also a current that is coming in. You have a finite Z in. You have a current gain of beta. So beta times IB is basically the value of your dependent current source. And then you have the same RO in parallel. Right? So that's how you model a BJT. So the only difference is that at the input side, you have a current input for a BJT. Now, you can also represent that as a voltage-controlled current source, because anyway, Thevenin and Norton equivalence is something that you already know that can be done. From a physics point of view, it should be modeled as a current-controlled current source, but you can forcefully model it as a voltage-controlled current source as well, because if there is a current flow, you'll know what is the voltage value across the input as well, and that becomes your input voltage, right? So you can always have the duality of Norton and Thevenin. So you can also model the BJT as a voltage-controlled current source, but from a physics perspective, it should be modeled as a current-controlled current source. So let's stop here. There are some practice problems after this, which have already been uploaded on Canvas, but these are just ungraded practice problems. In the next lecture, we'll start discussing about feedback.